All right, welcome back to chapter 7. We're going to dive into protein. I often joke that protein is kind of the overrated rock star in the world of nutrition, that kind of glamorous lead singer, lead guitar player in the band. Um, Protein is the most complex member of the macronutrient trio. And while protein is essential for health, most people who don't know a lot about nutrition tend to worry too much about protein without really understanding its role. So today we're going to dive deep into all the details of protein. So we'll start off with the science, the structure, the function, building blocks of protein, and then we'll move on to some practical things. How much protein do we need? What impacts does it have on our health? And what kind of food allergies and sensitivities are there out there related to protein? So, in every nutrition book I've used, I've taught Nutrition 101 for well over a decade now, gone through 4 or 5 different books with different colleges and universities. Every single nutrition book saves protein for the last of the three macronutrients. And that's because they're more complicated than carbohydrates and fats, certainly in structure and probably in the variety of functions as well, although that's a little bit more open to debate. So, protein performs a lot of essential functions, and you'll see the list here below. And we'll go over all of these in at least some detail, though to get the most detail out of all of this, make sure you carefully read the chapter. So, one example of protein function is maintaining normal fluid balance. So, fluid in the body is attracted to protein. So the presence and the distribution of proteins is part of how we maintain fluid balance in our tissues. One of these proteins in our bloodstream is albumin. And this is one that we get looked at very commonly when we get blood work done. Pretty much any blood work you get done at your healthcare provider will include looking at albumin levels. And from my work clinically, I'll tell you, I saw a lot of patients with edema, which is there in that the B picture, the swollen foot, that's swollen tissues. And pretty much every single time a patient had edema, their blood work showed abnormally low albumin levels. So when we talk about proteins, we have to start off by talking about amino acids. Amino acids are the building blocks of protein. And amino acids differ, or proteins differ from the other two macronutrients, carbohydrates and fat, in that they contain nitrogen. No other macronutrient contains nitrogen. Um, and we'll look at the specific structure of amino acids next. So every amino acid has a hydrogen atom. It has a carbon anchor. It has the amino group, which is the part that contains nitrogen. It has an acid group, and it also has a side chain. So here you see the side chain just says R group. And uh, the only part that differs between different amino acids is that side chain. So the rest of the structure is identical, but these side chains differ quite a bit, and those differences mean everything in terms of a protein's ultimate structure. And in biology, structure and function are always related. So the side chains are what determine what a protein becomes and what a protein does. Anytime you see the word essential nutrition, remember that means we must get it from the diet. So, in the previous chapter, we talked about essential fatty acids, right? Meaning that kinds of fatty acids that we could not assemble in the body. The same thing is true with amino acids. There are some amino acids non-essential ones that we can assemble in the body using other non-essential amino acids. We can swap out side chains. And then there are essential amino acids which we must consume in the diet. We're not able to make them or make them in sufficient quantities within the body. So we have 9 essential amino acids and 11 non-essential. So the non-essential ones we can produce as needed from essential amino acids in the liver. The amino acids with an asterisk mean that under certain conditions they become essential. An example cited in the book is that those recovering from injury are more likely to suffer a deficiency in the amino acid glycine. So that becomes essential with certain injuries and illnesses. So we're going to go back to the theme of functions of proteins. So one of the functions of amino acids is as precursors to form other compounds. So amino acids are not only building blocks of proteins, they're also building blocks of other compounds that contain nitrogen in the body. For example, epinephrine, that's the hormone that's part of the fight or flight response, that's made from amino acids. Histamine, which plays a role in um, the immune response, and also with allergy responses, that's built out of amino acids. And serotonin, another one that's a neurotransmitter involved in mood regulation. So if you think of the famous example, everyone being relaxed at Thanksgiving, eating a bunch of turkey. Well, turkey's high in the amino acid tryptophan, so our body can then make a fair amount of the neurotransmitter serotonin, which is kind of a relaxing neurotransmitter. Protein structure is quite complex, so we'll look at it bit by bit in several different slides. This is one way to think of at least the beginnings of protein structure. Some nutrition textbooks talk about protein alphabet. Instead of 26 words, there are 20 amino acids that make up the protein language. But however you want to conceive of it, the first step in constructing a protein is just the sequence of what amino acid is next to what amino acid. Our genetic material is essentially like software. So DNA has the recipe book. It has the software that can direct the machinery of the cells and how to construct the proteins that our body needs. So if we dive down into how each bead in that beaded chain of proteins links up together, we're zooming in the specific area that's shaded in green there, where the hydrogen of one amino acid meets the acid group, oxygen and hydrogen, of another amino acid. In protein formation, these atoms then drop off. So we have hydrogen, H2O, right? Two hydrogen and oxygen as water, they leave, and the rest of the amino acids fuse together. So the two amino acids are linked up and that water molecule is released. Just some basic, easy definitions here. Peptides are two or more amino acids together. Polypeptides are longer chains, proteins that comprise 50 or more amino acids. And most proteins are quite long, so they're mostly polypeptides. And once you get into a lot of amino acids linked together, you get into some pretty complex shapes, and we'll take a look at those. But they're coils and folds in three-dimensional shapes with 4 levels of structure. So the primary structure of protein is just that linear chain. It's what amino acid is followed by what other amino acid. The secondary structure of the protein reflects the coiling of the polypeptide chain and the specific shape that takes place is due to the chemical attractions between certain components of the amino acids, of the side chains. The tertiary structure is the final three-dimensional form of the protein. And in some proteins, you get two or more of these tertiary structures that associate with each other to form larger complexes. So that would be, not every protein has a tertiary structure. Some have it, some don't. And we'll take a look at some examples. So here you're looking at two proteins. The first one just has tertiary structure, and then you get a couple proteins together that have tertiary structure, and how they interact and link up together, that's a quaternary structure. So they form one larger protein. The classic example is the molecule hemoglobin, which is the major protein in red blood cells. That's comprised of an arrangement of four different polypeptide chains. So structure and function, right? These are concepts throughout biology. So the shape of a protein is what helps determine its function. So an example would be collagen. That's a fibrous protein with a unique triple helix structure, which results from the specific arrangements of amino acids like glycine, proline, hydroxyproline. This triple helix formation is crucial for collagen structure because it creates a strong and stable structure. In the skin, collagen provides tensile strength and helps maintain the skin's firmness and resilience. The triple helix structure allows collagen to form a dense network of fibers, contributing to the skin's ability to withstand stretching and deformation. Changes in the structure of collagen, such as alterations in the amino acid sequence or disruptions in the triple helix arrangement, can lead to conditions. For example, Ehlers-Danlos syndrome, where individuals experience hypermobility of joints and overly flexible skin due to defective collagen. So an example of shape influencing function, we can look at sickle cell anemia, which is a genetic condition characterized by abnormal red blood cells. Why are they abnormal? Because there's one amino acid that is incorrect in the sequence of amino acids, and that changes the shape of the protein. And instead of having that kind of donut-shaped red blood cell, we get a sickle-shaped red blood cell, and that means that that blood cell carries less oxygen, and it can also form clots a little bit easier. So we're going to go a little into protein digestion. And one of the steps in protein digestion is something called protein denaturation. So we can alter a protein's natural shape and function by exposing it to conditions like heat, acids, physical agitation. So for instance, um, just cooking eggs, right? You get this translucent looking protein, you add heat to it, and it becomes white in nature and firms up, right? And the stomach, hydrochloric acid, denatures food proteins, which helps make them easier to digest. Um, Cooking makes protein easier to digest, and then the stomach, we're also breaking down protein structure. Another example of this kind of acting like the stomach outside the stomach, if you ever make ceviche, you take raw seafood, let's say some raw shrimp, you add a bunch of lime juice to it, you actually begin the process of protein digestion. And shrimp are relatively simple enough in structure that you leave that shrimp in that lime or lemon juice for a while, and it's actually denatured enough that you can eat it right from there without cooking it. So the acid kind of cooks the protein. Looking into food sources of protein, typically people really think of animal flesh, like shrimp, right? Chicken, steak, and dairy products as well. But animal products as being kind of the foundation of protein. And In the US, it's true, we eat a pretty animal food source heavy diet, but in lots of parts of the world, including where I worked a lot in Central America, the vast majority of protein people take in are actually plant proteins, and they supplement some with animal proteins. And that's mainly because of the economic reasons. Plant proteins can be really inexpensive. Um, and we'll take a look at a few of these here. So, in much of the world, legumes are incredibly important protein sources. For instance, in a lot of Latin America, beans form a major part of people's protein intake, uh, as well as other legumes, lentils, split peas, depending on where you are. In Asia, a lot of soybean, that's also a legume. In India, lentils. Venezuela, they're pretty fond of lentils, but most of Latin America, mostly beans for the major protein. Peas are also a legume. Peanuts are actually technically a legume, although nutritionally their nutritional profile is more similar to a nut. Um, and nuts have protein, but nuts are about 70-75% fat, 20-25% protein or so. So while they have protein, they also have a lot of fat. Very healthy fats, but quite a bit of fat. This one I mentioned in an earlier slide, so we'll go ahead and skip this for now. These are important definitions to know the difference between high quality proteins and low quality proteins. And this seems like a bit of a dramatic difference, but if you get enough of lower quality proteins in the diet and the proper mix, for instance, you pair legumes with grains, make a complete protein, you can be very, very healthy without animal source proteins or with just occasional animal source protein. So this slide kind of makes it sound like, oh, everyone needs a lot of animal-based proteins. That isn't the case. What it means is that the animal-based proteins have all 9 essential amino acids in them, while the plant-based proteins do not. So they have to be paired with other plant-based proteins. Um, Although that doesn't have to be at the same meal within a day or so. So limiting amino acid, that concept is with people who have very unbalanced diets, and this does happen in the developing world some where certain economic political situations make it so that there are populations that, for instance, survive on a great deal of rice and not much legumes and very few animal foods. So they might have certain limiting amino acids that are in the legumes or the animal foods. Um, and so they have an incomplete diet. They're not getting sufficient amounts of protein. Most plant foods are not sources of complete protein. Quinoa, soy protein, those are exceptions, but any other bean, legume, nut, seed, grain on its own is limited. So that's why you have these traditional diets, like in India, for instance, where you have lentils and rice is a common combination. In parts of Asia, soy and rice. In Latin America, beans and corn. Those make complete proteins. All right, let's dive a bit into protein digestion. So nothing happens to protein in the mouth. Um, but in the stomach, we begin protein digestion. So the acid in the stomach helps break down some of that protein structure. So we go from the complex protein structure, and then we have a bunch of polypeptides that are freed up. They enter the small intestine, and there the pancreas secretes protein splitting enzymes that break down the polypeptides into shorter peptides and eventually into individual amino acids. So we're back in that same place in the small intestine where we always end up, right? The brush border of the small intestine with the microvilli, where we're going from digestion of food to absorption of food. So that final stage in protein digestion, we're going from these polypeptides to di and tripeptides. There are enzymes that are breaking apart these longer chains into smaller and smaller chains. And eventually the dipeptides and tripeptides, they can be absorbed directly by the microvilli. They're broken down a little bit further into individual amino acids, and then they can be absorbed into the bloodstream. In, so in protein absorption and transport, we have short peptides and amino acids. They're moved into the brush border cells of the intestine through the microvilli into our bloodstream via different specific carrier systems, which we don't get into in the Nutrition 101 class. And then after absorption, the peptides are broken down to the individual amino acids, and then they can enter our capillary system. This is a really useful slide just to summarize what happens in protein digestion. So in the stomach, the proteins undergo denaturation by stomach acid, and the enzyme pepsin comes in and does some breaking down of the long polypeptide chains. And the small intestine, then we get more digestion occurring, this time not in the acidic environment, but in the basic environment of the small intestine. And we get some of the uh, protein enzymes that come from the pancreas, including trypsin, chymotrypsin, which are further breaking down polypeptides into smaller and smaller units. Then in number three, we're at that uh, most critical place. We always end up the brush border of the small intestine, and we get the final digestion and then the absorption. We cross over into our capillary system, our cardiovascular system. Then in step four, we have the amino acids ending up in the hepatic portal vein and traveling to the liver. And step five's there, but actually very, very little dietary protein is excreted in the feces because protein is very biologically valuable, so the body holds onto it. So to summarize the concept of protein turnover, this is really important. Protein in our evolutionary history has not always been abundant, and in fact, sometimes very hard to get. So and still is in a lot of parts of the world. The human body has adapted to be very efficient with protein. We conserve protein, and we in fact recycle proteins in the body. So the body's always breaking down different cells of the body, reconstituting different cells. For instance, a few chapters ago, we learned that the cells in our digestive tract only live a couple days. Well, those cells have proteins in them, and we don't eliminate those proteins, we actually recycle those proteins. So anyone that consumes sufficient protein, and in the US it's fairly uncommon to be protein deficient. We eat very high protein diets here. But anyone who doesn't have a protein deficiency will have a substantial amino acid pool, it's kind of a bank, reserves that the body can draw on when it needs different amino acids. Some important definitions here. So deamination, so that's removal of the nitrogen group and turning it into an amino acid, turning an amino acid into a carbon skeleton. This happens when we consume more protein than we need, which, as I mentioned, is a pretty common phenomenon in wealthy countries and certainly in the US. So that excess nitrogen, once the deamination process has happened, that goes to the liver and that gets converted into urea, which is a waste product that we urinate out. In fact, there's some research showing that very high protein diets are pretty tough on the kidneys because, well, the kidneys are where that urea ends up, and it puts a burden on the kidneys when people eat 2-3 times their protein needs over many decades. That carbon skeleton can then be burned for energy or converted into other compounds. Transamination happens when the body makes non-essential amino acids For instance, to make the amino acid alanine, the nitrogen group is pulled off of glutamic acid and transferred to pyruvic acid. So we basically say this in the last couple slides, but we don't store excess amino acids. It's not like fat, where we store excess fat as fat, we store excess carbohydrates as fat, or actually we do store a few hundred grams of carbohydrates, but amino acids, we have that amino acid pool, but that's not a large quantity. Um, when we eat more protein than we need, those unnecessary amino acids undergo deamination. And this is just a nice little visual representation of a couple of the concepts I've talked about in the last few slides. So looking at a couple blood tests related to protein intake and kidney function, blood urea nitrogen is a blood test that is used to assess kidney function. An elevated Bun level occurs when when the kidney function is decreasing, kidney health is poor, and the kidneys are no longer able to filter urea from blood properly. So I actually worked a lot with kidney patients, and as kidney function gets worse, those patients are advised to eat a lower and lower protein diet to put less stress on their kidneys. And then eventually, if they go on dialysis, the opposite occurs. They need to eat a lot more protein because the process of dialysis removes a lot of protein from the blood. It's not a very efficient process. So both a high bun and a low bun have several different sources, and this is commonly how lab values work. They're an indicator of what may be going on in the body, but usually a physician will have to look at a whole bunch of different labs and physical symptoms and talk to a patient to determine what exactly is the cause of those high uh, bun levels or low bun levels. So, looking at a couple other functions of proteins in the body, we mentioned the fluid balance very early on, but we haven't mentioned yet the role of proteins in the immune system. So, proteins are essential for making the antibodies that are kind of like the police detectives of the immune system, helping us identify antigens or foreign bodies in the body so that our immune system can then attack them. Proteins are also crucial for acid-base balance. So it gets a little bit into the chemistry of proteins, but proteins are able to either donate or accept an extra hydrogen, which allows, for instance, body fluids, specifically, for instance, blood, to remain in a very tight, narrow pH range, which is essential for human health. So in this slide and the next slide, we'll look at the concept of nitrogen balance. Since protein is the only macronutrient that contains nitrogen, we can measure how much protein is coming in, coming out by looking at the overall balance of nitrogen. And some key concepts here are the three states of nitrogen balance. So positive nitrogen balance means that we're intaking more protein or nitrogen, you can use the words really interchangeably here, then we're losing. So this happens when the body's adding tissue. So growth, pregnancy, recovering from illness and injury, like putting weight and muscle back on. Um, and that happens in resistance exercise. So building muscle, for instance, you're in positive nitrogen balance. Nitrogen equilibrium, that's where most healthy adults are at. So the protein or nitrogen intake is equal to the protein or nitrogen losses. Negative nitrogen balance, that's usually associated with not desirable states. So being really sick, bed rest, fevers, injuries, burns, um, increased protein losses resulting from kidney disease or blood loss, loss of muscle tissue, also negative protein balance. So the AMDR for protein is 10 to 30% of total energy intake. That sounds like a pretty wide range, but people's protein needs vary, and one can be very healthy anywhere within that range. So, a way to calculate protein needs for a healthy adult is to do zero point 0.8 grams per kilogram. So, for instance, myself as an example, I'm 150 pounds. I would divide by 2.2 to get my weight in kilograms, 66, and then I would multiply that by zero point 0.8, and I get about 55 grams of protein. I exercise, but not a lot, so I really don't need an elevated protein intake. Um, to give you an idea, well, we'll go a bit more into protein intakes, but a typical deli sandwich you might get, like a chicken or turkey sandwich, that will have at least 30 grams of protein, sometimes even 40 or more grams. So it's pretty easy to meet typical protein intakes, especially if you eat any animal products at all. And the average American eats quite a bit more than the RDA. Where we need to be a little bit more careful about protein intake is with plant-based diets, which can be fantastically healthy, but we have to consider what are our sources of protein and make sure we're meeting protein intakes. So, if you're eating a vegan diet, especially, it's almost impossible to meet protein needs or have a healthy vegan diet without legumes. So, legumes being different kinds of beans, split peas, lentils. Those are just about essential for a vegan diet. Vegetarian diet can be a bit more flexible because you're getting some protein from dairy products as well. But complementary our proteins are some of those combinations we mentioned earlier. So two different plant foods that meet each other's deficiencies in essential amino acids. So classic example would be beans and corn, which was the staple of much of the Americas, even some of North America, particularly the Southwest, but Mexico, Central America, staple for thousands and thousands of years. So the average American is taking in about 15% of our calories from protein, but we also have to remember that the average American is also over consuming calories, right? We have two-thirds of Americans who have a overweight or obese, and we are consuming more calories than we need. So that 15% doesn't sound like a lot of protein, and it wouldn't necessarily be if it was 2,000 calories a day, but when it's quite a bit more, the protein numbers go up, right? So a high protein diet provides an amount of protein greater than the RDA, so more like 20 to 35% of calories, so on the upper end of that AMDR. And achieving high protein intake from animal food protein sources is more common than solely from plant food protein sources because the plant protein sources aren't as concentrated. Now, those plant protein sources come with a lot of fiber and water and phytonutrients. In contrast, the animal food sources are often high in saturated fat, fair amount of cholesterol, and obviously no fiber or phytonutrients. So, a little bit more risky to be getting a great deal of animal protein in the diet. This slide provides a good breakdown of some of the pros and cons of high protein diets. High protein diets are often kind of sold, or you could say oversold, as a great way to lose weight. Protein is very satiating, but you don't necessarily need a lot. And if you're not choosing lean proteins, that's not going to work out super well because you'll be getting a lot of that calorie dense fat along with the protein. Disadvantages include kidney stress, and that is one of the theories behind why we have so much kidney disease in the US. We eat high protein diets. Um, and the cardiovascular risk that comes along with that excess fat. Also, if you're eating more of your calories from animal sources, it's hard to meet your fiber needs. And if you're not meeting your fiber needs, um, you're putting your digestive tract at a bit of risk, especially for colorectal cancer. And then there's a possible link with bone health that um, high protein diets tend to increase the urinary excretion of calcium. So positives and negatives in these protein diets. One of the interesting things about nutrition is that it intersects with so many other disciplines and areas, and what we eat has a tremendous impact on our ecosystem because that's the major use of land around the world is for production of food. The issue with eating a lot of animal foods is we have to feed those animals and to allow them to grow to proper size where we can then slaughter them for their meat or milk them for their dairy, right? It's not that efficient when compared to simply using land for plant foods that we can eat because if you think of a farmer, for instance, who has just a few acres, they can either use those few acres to graze some cows, um, or they could use those few acres to raise a great deal of corn and beans and other vegetables. So the amount of calories you can produce for land that is producing plant foods is quite a bit greater than the amount of calories you can produce from land that is producing animal foods. So protein deficiency is not common in the US, and I'll say in my clinical work, the only times I saw it in general were folks who had a lot of other health and life challenges. For instance, drug and alcohol addiction, eating disorders. Sometimes people are homeless who don't have access to a kitchen. So in the US, less common, pretty uncommon. Worldwide, though, yes, um, it's a major issue. And one of those reasons, as mentioned earlier, raising animals takes a lot of land. So uh, people living off these plant-based diets, if they're not getting enough legumes, nuts, and seeds, if they're living mostly off grains, it's pretty difficult to meet protein needs. So protein energy malnutrition takes two common forms. In marasmus, that lacks both all, all macronutrients, all calories and nutrients, and also protein. And that's kind of a skeletal form of malnutrition. When you can see people's rib cages, that kind of thing. Kwashiorkor is undernutrition that's specifically from lack of protein. So there's enough calories, but there isn't enough protein. And often you'll see swollen cheeks, arms, legs, belly, and that's due to the edema because there isn't enough protein to manage fluid balance well. Another kind of third hybrid form is marasmic kwashiorkor, which is when someone who has had kwashiorkor then starts not to consume enough energy, and then there's edema and wasting. And wasting is when uh, your body essentially starts catabolizing itself, breaking down organ and muscle proteins to obtain sufficient amino acids for survival. So here's a visual representation. That tragic skeletal figure is marasmus because there's not enough energy and there's not enough protein. The figure who has the swollen belly is kwashiorkor, or there's some sufficient energy but not enough protein, so they get the swollen belly and likely swollen feet, where you can see there the edema in the feet and the belly. A food allergy occurs when the body treats certain proteins from food as foreign organisms, as antigens. And that triggers an immune response, and that immune response causes symptoms of allergies. It's thought that about 10% of the population has food allergies, and it seems like that is more than in the past, and whether that's due to factors in our diet and lifestyle, poor digestive health, or possibly due to improved diagnosis, this is up for debate. Some allergies can be so severe that just microscopic small amounts floating through the air or on a seat or a plate can cause a severe reaction. So, in enclosed areas like buses, airlines, this can be an issue. Food allergies can take a lot of different forms. This slide shows some of the more common reactions. Typically, when I've worked with people around food allergies, what I have them do is write down everything they're eating, keep a food diary, and then write down a diary of symptoms and keep an accurate time log so that you can connect what different foods go with what different symptoms and see if there are patterns, because of course you can get diarrhea from or vomiting from something that isn't necessarily a food allergy, right? Mild allergic reactions generally occur within 30 minutes to a couple of hours of eating the offending food, which can sometimes make diagnosis a little bit difficult, but anaphylactic reactions can occur within just a few minutes of allergen exposure. So that makes diagnosing it, what caused the reaction, easier, but it also means that these can be life-threatening reactions. Anaphylactic reactions are very serious. People who have anaphylactic reactions typically carry medication with them that can prevent coma or even death, can prevent anaphylactic shock. I mentioned one way of diagnosing food allergies, which is keeping a food diary and then keeping a log of symptoms and working with a dietitian around that. There's also skin patch testing, where just little bits of the proteins of the food are applied to the skin to see if there's a reaction. And that has been shown to be a reliable way of identifying allergens. A few chapters ago, you read about the regulations for food labels, and one of the changes that was made a couple of years ago was that food manufacturers must identify potentially allergic ingredients on product labels. So that helps people avoid food allergies. The other area where food allergies is a big issue is when people are eating outside the home, so eating in cafeterias and restaurants, and it just requires a lot of caution, talking to wait staff, talking to the chef, and making sure that you're not exposing yourself to a food allergy. These top 8 food allergens account for about 90% of all food allergies in the US. This is an example of what that food label requirement looks like. So down there in the list of ingredients, at the end of the list, the manufacturer identifies common food allergens. Celiac disease is an autoimmune disorder in which a person's immune system reacts to the protein gluten that's found in wheat, barley, and rye. Um, wheat is so omnipresent in the Western diet that it can be challenging for people with celiac disease to avoid wheat, but it's very much necessary because when a person with celiac disease intakes food with wheat, they have a variety of very unpleasant symptoms. I'll cover those symptoms in the next slide, but important to know that celiac disease is distinct from a food allergy because it's actually an autoimmune response. So the body attacks itself when gluten is consumed. And that damage goes right to that most critical point that we've talked about so many times in the semester, to that brush border of the digestive system, to that intestinal villi. Uh, and when that is damaged, the issue is not only does someone with celiac disease have very unpleasant symptoms, but they can't absorb nutrients well. So they can also suffer from nutrient deficiencies. Since celiac disease is um, a disease of the intestinal system, you can imagine, well, there's a lot of symptoms related to intestinal function: abdominal pain, gas, bloating, diarrhea. And if you're absorbing nutrients very poorly, you can end up with poor growth and people are still growing, under 20 years old or so, weight loss, and other diseases of deficiencies, for instance, anemia, osteoporosis, liver disease, even forms of intestinal cancer and dementia. So celiac disease can be quite serious. There is no cure for celiac disease, so the only treatment is following a gluten-free diet, which has its challenges because there's particularly wheat in a lot of products, not so much rye and barley, but wheat is very widespread in the Western diet. And the issue is also that the facilities where food is made, if a product that doesn't have gluten in it is made in the same facility as a product that has a lot of wheat and gluten products in it, it can be contaminated with trace amounts of gluten, and for some people, that will still trigger um, symptoms. So it depends how sensitive the person with celiac disease is. But for that reason, for instance, you'll see on oatmeal containers. Now, oatmeal doesn't have gluten in it, but oats could be stored in the same grain silos as wheat. So some manufacturers of oatmeal will put gluten free, like no traces of gluten. It's been that oatmeal was harvested and stored in places where there was no cross contamination with wheat. When someone has celiac disease, hopefully they get the opportunity to work with a registered dietitian because it can be a little bit tricky for the average person. It's not as if gluten is listed necessarily on labels. So you might see something like wheat bran, farina, seminola flour. These things are all wheat-based foods, and so they have gluten. But if you're not well educated in nutrition, you could easily miss that. Luckily for people with celiac disease, there are a lot of substitutes for wheat, barley, and rye. Corn, for instance, quinoa, rice, brown rice, wild rice, um, lots of different grains that still um, really tasty, inexpensive, and gluten free. So some people don't have celiacs, but they have a gluten sensitivity. So when they eat products with gluten in it, they feel some digestive discomfort or sometimes some other symptoms. Usually this is fairly dose dependent. So I've had a lot of patients where, yeah, one slice of bread is fine, but they can't eat two slices of pizza. That's too much, and they'll really get symptoms from that. With the gluten sensitivity, there are some tests that can be done: blood antibody testing, internal biopsy, followed by food provocation test. But you can also just keep a food diary, keep a log of symptoms, and see if foods that containing gluten are triggering symptoms or not. This can also be a good way of determining other food allergies, for instance, an allergy to dairy foods or to shellfish. When gluten-free diets first became kind of a big thing well over a decade ago, there were a lot of health influencers, bloggers, and various social media influencers who were really heaping praise on gluten-free diets. And for people with celiacs, it's absolutely necessary. For people with gluten sensitivities, it's very much necessary, very helpful, but doesn't necessarily make a difference for other folks. And the other issue is that foods that are gluten free are not necessarily healthy or nutrient dense. If you're replacing bread and Cheerios and different kinds of cereals that have wheat in it uh, with something like brown rice and oatmeal, great. But if you're replacing those with highly processed foods, might not be a great choice. I mean, there's a lot of gluten-free cakes and cookies out there that they're still cakes and cookies. They're not nutritionally beneficial, regardless of the presence or absence of gluten. So a couple good tips there for following gluten-free diets. One thing I've noticed recently in the last couple of years, um, the hard seltzers have become more of a trend, and I think that's because a lot of people out there have gluten sensitivities, and if they drink a beer or two, especially along with a meal that might also have gluten in it, it really adds up and results in some symptoms. But there are a lot of options out there for gluten-free diets or very low gluten diets for those who are sensitive but not celiacs. A couple good tips out there for people following gluten-free diets. Um, just to mention here, this is also really important that gluten-free, yeah, often promoted as healthier or great for weight loss. Um, all gluten-free means is that it doesn't have gluten in it. So you can have a very healthy, nutrient-dense, moderate, or even low-calorie diet that's gluten-free, and you can also have a gluten-free diet that's really junky. So the term gluten-free doesn't mean anything regarding health other than there's no gluten. Well, since we're on this topic of food allergies, we may as well cover food intolerances, which is related. Conditions characterized by unpleasant reactions following the consumption of certain foods and non-protein foods. For instance, we talk about lactose intolerance in the carbohydrate chapter, monosodium glutamate, which is in a lot of foods. For some people, causes no reaction. For some people, yes. Likewise, caffeine for some people causes irritability and insomnia. For other people, not at all. And then there's also short chain fermentable carbohydrates. Um, which I believe we did cover a little bit in the carbohydrate chapter, but some people get a lot of unpleasant digestive symptoms from consuming those, and other people makes no difference. There's a lot of variation in human biology. So, the non-celiac gluten sensitivity is considered to be an example of a food intolerance because it's not necessarily an immune response. It's just that the body doesn't tolerate the gluten very well. Um, and some of those symptoms in food intolerances can be somewhat similar to allergies, migraines, skin rashes, asthma, fatigue, and various digestive disturbances. Phenylketonuria, or PKU, that's a rare genetic metabolic disorder. It affects maybe about one to every 10 to 15,000 infants in the US. And testing at birth is really important because um, if phenylalanine is not avoided in those early few weeks of birth, that infant can develop intellectual disabilities during the first year of life. So phenylalanine is actually one of our 9 essential amino acids. The body can convert phenylalanine into the non-essential amino acid tyrosine, but in some people there's a lack of the enzyme that makes that conversion, and you can get an unhealthy buildup of phenylalanine, and that is people with PKU. Because of the connection with poor growth for infants, all newborns undergo blood testing for PKU, and of course, several other inherited diseases. Since phenylalanine is essential for growth and development, even those with PKU need at least a small amount. They just have to have a very controlled amount. And there are special infant formulas available, and as the child grows and matures, um, there are special low phenylalanine diets that can be followed for folks with PKU. So, some important definitions when it comes to plant-based diets. Vegetarian diet means that um, there could be some dairy products in that diet. And a vegan diet is absolutely no dairy products, so only plant-based foods. So, some of the other definitions to know here. What a lot of dietitians dealing with people with chronic disease try to promote is not necessarily a vegan or vegetarian diet, but just semi-vegetarian or just cutting down on some animal foods and incorporating more plant-based proteins. And the reason for that enthusiasm around plant-based diets, especially with dealing with folks with chronic disease, obesity, and even certain cancers, is that vegetarian diets are often lower in saturated fat and calories, and they also contain a lot of fiber, which has a lot of health benefits. So I mentioned a couple of these advantages here. Um, the possible disadvantages: B12 comes from animal source foods, although there are traces in it in a few vegan foods like nutritional yeast and seaweed. Low vitamin D, although you can get that from the sun. Relatively low riboflavin. Zinc, iron, and calcium can definitely be issues in strict plant-based diets. So if you're following a plant-based diet, you're going to want to think specifically about some of these foods and what your sources are. Sometimes that means taking supplements, but sometimes that also just means looking at consuming certain plant-based foods that have some of these rare nutrients. I mentioned two examples, nutritional yeast and seaweed, which are good sources of vitamin B12 and a couple minerals. And another possible disadvantage is when you're eating a plant-based diet, sometimes there are challenges in getting enough calories in because plant-based foods are lower in caloric density than animal-based foods. And for that reason, where we need to have the most caution with plant-based diets is when people are young and growing, because if you're feeding a child a plant-based diet and you have a whole bunch of broccoli and beans and a couple of ears of corn on a plate, children can get full very quickly because there's a lot of volume in these plant-based foods. So they might not be able to take in as much energy, as much calories as they need for their growing bodies. In the US, we tend to eat a pretty calorically dense diet, so this isn't generally an issue, but with strict plant-based diets, it's something to keep a lookout for. Another life stage where we need to have some caution around plant-based diets is with pregnancy, because when a woman is pregnant, her caloric and nutrient needs rise. So, um, can definitely follow a plant-based diet, but want to make sure that there's enough calories and nutrients coming in. And I've worked with a couple of patients like this, and sometimes it's a matter of just adding a nutrient-rich smoothie once a day. Not necessarily something complex to fix, but something to keep in mind. One of the keys around plant-based menu planning is making sure you have a protein on the plate. So, something that frustrates dietitians and people in public health to no end is that a lot of restaurants don't really understand what it means to offer a vegetarian food meal. So that vegetarian meal needs to have some sort of significant protein source. Usually, the best choice is a legume. So, beans, lentils, split peas, they have significant quantities of protein. Nuts and seeds can also work as well, but to offer just spaghetti and marinara sauce with a side salad and say it's a vegetarian meal, that's an example of poor menu planning because that isn't a complete protein and doesn't have a significant amount of protein in it. So going with this pasta example, you could take that pasta sauce and if you add some cheese to it, then you're adding a protein source. Or in another example, lasagna, which is another form of pasta. So you have a vegetarian lasagna, you have a bunch of great vegetables in there, and then you add a legume, tofu. Tofu has a lot of protein in it, and maybe even cheese, and then you're going to have plenty of protein. Grilled vegetable kebabs coming with rice and black beans. So the rice and black beans form a complete protein. Um, you can think of, our famous big American Mexican style chain Chipotle's, right? In Chipotle, there's quite a few vegetarian options that have complete proteins because the burrito shell is wheat, which is a grain, which has some proteins from grains, and the beans, legumes. Then you have the other proteins the grain is missing, and then you have a complete protein together. And same with bean and corn tacos. The plant-based trend has resulted in a lot of food science around making better veggie burgers. They're certainly better than 20 years ago or so. And we have, Impossible Burger and Beyond Burger, which taste quite good and have a fair amount of protein in it. So they are good options. The only thing I'd mention about those is they do tend to be pretty darn high sodium. So a little bit of a drawback on that, but if you're not getting a lot of other high sodium foods in your diet, then it's not a bad choice. So we end this chapter looking towards the future and some very current science. Nutritional genomics. So, two major components of this nutrigenomics, the study of how nutrients affect the expression of a person's genome. So, we have that software or genetics, but the kind of nutrition we take in, it changes how that software is expressed or deployed. And then nutrigenetics, which is the study of how inherited genetic variations influence the body's response to specific nutrients and nutrient combinations. One thing I've found working clinically is it's really interesting how there is no one perfect diet, and there's a tremendous amount of variations between individuals, and some of that has a genetic basis, which is some of what nutritional genomics explains very well. And by the way, not just nutrition, but I'll have two patients who are very similar that both have high blood pressure, and one needs 30 milligrams of a blood pressure medication, another needs 10. So our bodies process drugs differently, our bodies process nutrients differently. This area of nutrition, I think, points out one, how interesting nutrition can be, but also how it can be kind of frustrating because you can have a low fat diet for one person be very effective, lowering the blood cholesterol, maybe lowering weight, maybe causing all sorts of positive consequences. And for another person, they follow a low fat diet and has no effect on their cholesterol or and no effect on their weight. Another example from the book, excess vitamin C can cause kidney stones. It does in some people. It may contribute to the development, but other people can take large doses of vitamin C every day and never develop a kidney stone. So, part of this is everyone's genetic code is different. So, what this all points to is the concept of personalized nutrition, which has really been always a dietitian's role, but we haven't had um, as much information on how different genetics can influence someone's results following different diets, for instance. The hope is that personalized nutrition based on this new information can promote greater improvements in health than more universal dietary recommendations. An example of where this is going is there are some biotech companies out there that are selling at-home genetic test kits, and the idea is that you give a saliva sample and mail it to the company for analysis, and then they develop a health plan based on your personal genetic makeup. Actually, a friend of mine from graduate school was involved with one of these companies for a couple of years. Unfortunately, eventually the company went bankrupt. It's probably a little bit early right now to be doing this kind of work, but it's quite possible this is going to be a significant part of the future of nutrition. I would recommend to people considering going into the nutrition field to take courses in genetics and nutritional genomics because this will likely be an influence in the near future of nutrition. Okay, well that's it for chapter 7 protein. Make sure you read the book carefully because this PowerPoint narration is just a way to kind of refresh and assist in the learning process. It is not a substitute.